In this section, we're going to look at chapter 5 and start introducing some of those continuous probability distributions rather than the discrete probability distributions. So the one we're going to focus on, and the one that tends to be most common, particularly in introduction courses to statistics, is the normal distribution or the normal curve. And we've seen it a little bit so far, but we're going to go into a lot more depth in this chapter and really learn how to work with it. In chapter 4, we distinguish between discrete and continuous random variables and learn that continuous random variables have an infinite number of possible values that can be represented by an interval on a number line. Its probability distribution is called a continuous probability distribution, and that's what we're focusing on in this chapter. In this chapter, we'll learn about the most important continuous probability distribution in statistics, which is called the normal distribution, and you'll also see it referred to as the bell curve. Normal distributions can be used to model many sets of measurements in nature, industry, and business. So for instance, blood pressure of humans, the lifetime of smartphones, and even housing costs are all normally distributed. So there's actually a lot of variables in the world that are naturally normally distributed, meaning that they have this nice bell-shaped curve to them. Other examples tend to be heights and weights, are often frequently normally distributed as well. So there's a lot of items that just naturally follow this pattern, and it tends to be a very common one. Now, there are other continuous probability distributions as well, but we're going to focus our time really on that normal distribution. So the normal distribution is a continuous probability distribution for a random variable x. The graph of a normal distribution is called the normal curve. And again, you may have also heard this as a bell-shaped curve. What happens in a normal curve, so in a perfectly normal distribution, the mean, median, and mode are all equal, so they're all that center value here. The normal curve is bell-shaped and symmetric around the mean, meaning bell-shaped, so it kind of looks like a bell. And it is symmetric, meaning you have a nice mirror image around that mean. The total area under the normal curve is equal to 1. So we talked about this a little bit in the last chapter when we were doing discrete probability distributions. So we were kind of looking at those histograms and noticing that the bars of the histogram were related to the area, of the bars of the histogram were related to the probabilities. So this idea of area and probability has a very close relationship, and we see that here. So the area under the curve is actually equal to 1 because the total area under the curve represents a probability here. And with continuous curves, remember that values can be anything within an interval. So it's not going to be like a discrete probability distribution where we have a table, because I can't list every single value. It's not possible with continuous curves. So we use area a lot more here. So this area under the curve is equal to 1 because it actually represents the total probability. The normal curve approaches but never touches the x-axis as it extends further and further away. So it's a little hard to see here, but this curve actually will get closer to the x-axis but never touch or cross it. So it's always above the x-axis. And then between the mean minus the standard deviation and the mean plus the standard deviation, the graph curves downward. The graph curves upward to the left of the mean minus the standard deviation and to the right of the mean plus the standard deviation. The point at which the curve changes from upward to downward is called an inflection point. So in algebra courses, you may have heard this as going from concave up to concave down. So for instance, something like this is concave up, and something that's this shape is concave down. And these inflection points occur when you change between concave up and concave down. So on the graph, you have an inflection point here and here. So what's happening is right here, you can see that we're concave up, so it's more of a U shape, like a regular U shape. And then it flips to concave down, so an upside down U, and then it flips back to that regular U shape, concave up. So your inflection points are where it changes direction there. And they're specifically at the values, the mean minus 1 standard deviation and the mean plus 1 standard deviation. So it's good to know where those inflection points are. And just like we've seen before, when we're talking about this normal curve, that center here, it's also the median and the mode, but really what we care about is the mean. So that center is at your mean here. And then each of these lines goes out by 1 extra standard deviation. So you have plus or minus 1 standard deviation, plus or minus 2 standard deviations, and plus or minus 3 standard deviations. I know it's a little hard to see on the handout, so if you go to your book, you have a nice clearer image there. But just like we've seen before, when we've done other applications of that bell-shaped curve, we're always kind of adding those standard deviations on here and using that mean as our center. You've learned that a discrete probability distribution can be graphed with a histogram. And so for a continuous probability distribution, you can use a probability density function, which is abbreviated as PDF. And a probability density function has 2 requirements. 1, the total area under the curve is 1, and 2, the function can never be negative. So this outer curve right here that makes that bell shape is actually a probability density function. And the formula for it is given right here. Now, you don't need to know this formula. We're not going to work with this formula, but those who go into higher level statistics may need this formula, or if you're doing it more by hand. So those who are math majors oftentimes will use this formula to actually compute the areas using calculus and integrals and things like that. So we're not going to do that here. We're going to rely on technology to help us and tables and things. But that curve is basically how they get that outer graph. It's using this equation right here, which obviously can get pretty complicated. So for us, like I said, we're going to rely on technology. We're going to rely on tables to help us find values. But if you were in a more math-based, like math major-based course, using calculus and things like that, we actually can use that curve with calculus and integration to find areas. Now, a normal curve can have any mean and any positive standard deviation. The 2 parameters, mean and the standard deviations, remember those are our Greek letters for the population, mean and standard deviation, determine the shape of the normal curve. The mean always gives the location of the line of symmetry, so that's the center as well. And the standard deviation describes how spread out the data is. Oops, let's focus this. So here are 3 examples. Now in the figures below, they all have the same mean. Oh, sorry, excuse me. Curves A and B have the same mean, and curves B and C have the same standard deviation. So the first 2 have the same mean, excuse me, and then the second 2 have the same standard deviation. But you can see how things change. The total area under each curve is 1. So we do have that probability distribution here. And also in each graph, one of the inflection points occurs. 1 standard deviation to the left of the mean, and the other one occurs 1 standard deviation to the right of the mean. So you have the same general features. So they're all centered about their mean. They all have inflection points, 1 standard deviation out from the mean in both directions. Here, let's look at the first 2 for a second. We can see that they have the same mean, so they both are centered on that value 3.5. The standard deviation for the first one is 1.5. And the standard deviation for the second one is 0.7. And you can see that when you have a larger standard deviation, your graph is more spread out. When you have a smaller standard deviation, that graph is more clustered closer together. So even though they have the same mean, they have very different shapes. This one is more spread out because of the larger standard deviation. B and C actually have the same standard deviation, which is why you see very similar shaped curves there, but they have different means. So this one has the mean of 3.5. This one has a mean of 1.5, so you can see that their centers are at different locations, but because they have the same standard deviation, they have much similar shapes. All right, so let's do one example with that. So we have 2 normal curves here, and we want to know first which normal curve has the greater mean. So remember, your mean is your center, and it also gives that line of symmetry, so that mirror image line, so where the graph looks the same on either side. So for graph A, if I go down here right at that center, I can see that the mean is 15. Whereas for B, again, if I go right here at that center, I'm seeing the mean is 12. So which normal curve has a greater mean? Well, A does, right? So that center of that curve is further to the right. So the value of 15 is larger than 12. Okay, so for the first one, it's graph A. Now, which curve has a greater standard deviation? So for your standard deviation, that's about the spread of the data. Okay? And the larger the standard deviation, the larger the spread of the data. So if I look at my two curves here, I can see the A curve, right, is pretty tight together. So it's very close, a lot of that data. Whereas the B curve is a lot flatter. It's a lot more spread out. So that B curve has more spread. So it has a larger standard deviation. So the answer for this one is B.